of slow roll into this. Two types of bonds, ionic bonds, covalent bonds. We'll find out there are more than just those two types of bonds, but these are our easiest kind of cutoffs. These are also going to be the cutoffs that we'll use for your very first assignment after the exam on Thursday, which will be nomenclature, how to name compounds. And you will subcategorize those compounds into ionic compounds and covalent compounds. So the rules will kind of change for how you go through and name things. So you need to be able to identify that an ionic bond is a metal and a nonmetal. Covalent bonds are two nonmetals. Do we need to worry about a metal-metal bond? No. Is it different from these? Yes. Why do we not worry about it? We don't want to deal with it. Pretty much the answer. Right? So you don't have to stress about it. If you were going to take more kind of engineering, inorganic chemistry type stuff, you'd probably look at those metal-metal bonds. Your ionic bonds get split into cations and anions. The cation is typically the metal, but it does not have to be a metal. And your anions are your negatively charged species. Those are typically your nonmetals. Okay, so it's just a question of putting those two pieces together. Okay? Our covalent compounds, the interactions between them are a lot more complicated, which is why we end up with the Lewis structure rules. We could apply these rules out to ionic compounds, but the rules kind of break apart a little bit and they don't quite apply as well. So when we're talking about Lewis structures, we're really talking about covalent compounds, so taking two nonmetals. The rules listed here, I know it looks like there's a lot. There really isn't that many extra, I would per se, than any other kind of method out there. Okay? However, these rules are different in their approach to how you build a structure. Okay? If you learned how to draw a Lewis structure from somewhere else in the past, you probably learned a flawed process. Okay? That flawed process allows you to get to an answer. Okay? And it could even be the correct answer. However, the process behind it gets you a structure or an understanding of that structure that does not work well in future chemistries, particularly organic chemistry. So if you have to move forward through organic chemistry, these are what you should use to build your structures. If you don't need organic chemistry, then you don't have to use my rule sets, and you can use whatever rule set you want with some kind of big caveats. The biggest one being this rule of octets. Okay? The most amount of electrons we can have on any given atom is an octet. Just like an octopus with 8 arms, we get 8 electrons. Okay? We do not have any explanation for why we would exceed the octet, so you are not allowed to exceed the octet. Okay? If you do so, you will lose points. Okay? The only reason you would do so would be because you looked up the answer on the internet. The answer on the internet doesn't provide you the extent of where your knowledge limit ends, and so you don't know why one answer is correct or not. Okay, so be careful with looking at stuff on the internet for Lewis structure in particular, because Lewis structure has multiple tiers within it. The internet's going to show you the highest level knowledge tier. You don't need that. Okay? The next big kind of summary that comes out of chapter 12 is our shape summaries. You have to know all of those shapes and how to interpret it. Okay, so that all needs to get memorized. Okay, just like the rules for Lewis structure, these need to be memorized so that you can use them to evaluate a structure. Okay? What we have right here are now some examples, okay, that we will work through together as a class. Okay, but before we do that, I just want to cover the last slide because I know we talked about it really late. Okay? In fact, I think most people were walking out the door. I'm not blaming you. Actually, I shouldn't have done that. So if we go through and look at this, this is what I would recommend that you purge onto the exam. Within the first 5 minutes of the exam, your brain is probably holding on to the most amount of raw facts that you will have in your brain for the span of the exam. Okay? meaning the number of facts at the beginning of the exam that you know versus the number of facts that you know at the end of the exam, is at its highest. At the end of the exam, you will probably forget things. Okay? So in the first 5 minutes, if you can purge this information onto the test, in the last 5 minutes of the exam, you don't have to remember it. You just have to remember that you wrote it down, and you just use the information you wrote down. Does that make sense? 2 people are saying yes, the rest of you are just staring blankly at me. Okay. So the people that are saying yes will get all those answers right. The other people can stare at me blankly during the exam too. Okay? So, things that should get included on it. Identifying that the Roman numerals at the top of your periodic table correspond to the valence electrons. Okay, that applies for everything within that column. That's kind of a big deal. Okay? Electronegativity, okay, shown in blue, increases as we go left to right, and it increases bottom to top. Okay? The red one was ionization energy. We're removing that from this exam. It'll show up in exam 2. So don't stress about ionization energy. Atomic radius increases down a column, and it increases right to left. Okay? If that information gets copied onto the exam right away, you don't have to think about it or hold on to those trends, and you can answer the questions when they pop up in the exam by just flipping to where you wrote the information down. Make sense? Okay. Little test strategy 101. Remove the first page of the exam. The periodic table's on the back of it. Write your information there. Keep that out in front of you. When you're going through the rest of the exam, the periodic table is directly in front of you. You don't need to worry about looking anywhere. It's right there in front of you, along with the extra information you've included on it. Okay. The next part is taking the exam, actually answering questions. Which question should you start with? I heard the written questions. I heard number 1. Anybody else want to throw out an answer? All of those are wrong answers. Which question should you start with? The easy ones. How do you know it's easy? What's that?
If you know the answer.
If you know the answer. So you read the exam. Read through it cover to cover. At least skim it. Okay? Find the questions that are easy for you to answer. You now have guaranteed right answers. If you wait to find those during the exam, you will increase the odds of you getting it wrong when you should have gotten it right. Save the hard questions for the end of the exam. Okay? If this method is done properly, how will you feel at the end of the exam? Horrible. Why would you feel horrible? You're like, dude, why do I want to feel horrible after an exam? I already feel horrible. What did you spend the majority of your time working on? The ones you didn't know. Okay? You will have forgotten about all the answers that you did know and got rid of out of the way, and all you're going to be thinking about is what you didn't get. Okay? That is how you should build it. You weren't going to get those questions right anyway, so who cares? Save them for the end. Make sense? Right. When should you take a test like this? Always. No test should you ever take in sequence unless you are forced to take it in sequence. It is very rare to take a test in sequence. Okay? For those who say, well, this is totally not true. That's not how it works. A lot of people want to go into nursing, right? Okay? When you go into a hospital, if you're the first one in line, you're the one that gets treated first, right? Okay? The person coming in after you just had a heart attack. Who gets treated first? I have a hangnail, man. I'm first in line. I deserve to be treated first. Okay? We prioritize. You have to prioritize exams just as much as you would prioritize outside of class. Okay? It's a big deal. Okay? Questions about that? Do you feel there's other information that you might forget during the exam? Some people are shaking their head. I think they're just shaking their head for the heck of it. But you might think there's information that you will forget. Write that down pretty much right away, too. Now you don't have to worry about forgetting it. It's there. You can use it. Make sense? Okay. So we all watched the Lewis structure video, right? Yeah? Okay. Most stressful thing ever? Wait till Thursday.
Okay. Did you use to get scantrons, or are you just doing the paper?
So back to the exams. I do require that you use a Scantron. I also provide a Scantron because I'm fairly certain right now I make more money than you. Okay? And that one's small enough I can afford it. I can't buy everybody a textbook. Okay? So I will provide all the Scantrons. Other questions? Okay. About the Lewis structure video, did anybody want to ask any questions? Something jump out of them like, what the hell was that about?
There was one thing towards the end about the octahedral form of the combination. Like when I was doing one of the putting it all together, all the octets were formed on the outside, but then we had two sides in the core atom that were filled, and I wasn't sure how to connect the.
Okay, so let's just pause, take a deep breath for a moment, because anybody else is like, what the hell's going on with this octahedral thing? Yeah, it kind of sucks, right? Octahedral, so we had 1, 2, 3, that would only be 4 sides, so that would just be a square. To get an octahedron, what do we need? Okay, wedge thing coming at you, dash thing going back. Okay, what we've got now is what's known as an octahedron, because it would have 8 sides if we drew out all the faces on that. We get 8 sides. Okay, and we have an octahedron. How many electrons would that be? If each of those lines represented a pair of electrons? 12. 2, 4, 6, 8, 10, 12. I agree, it's 12. Is that sending up any kind of alarm bells in anybody's head? Violates the octet rule. But you said I shouldn't violate the octet rule. Who's right? The video was built for everybody, not just you. Okay? Are you responsible for the octahedral form? No, don't worry about it. Okay? If you want to know more about the octahedral form, by all means, sit down with me and we can talk about it, because there are some interesting things that come out of it. Okay? But it is not something you need to worry about for this test or for anything in this class. Okay? You are concerned only about the octet. To get octahedral, we must exceed the octet. You don't know how to do that yet. Other questions jump out at you?
This might have been just really late when I did it, but the formal charge, like how to make sure that it's done correctly.
I like that too, because formal charge is one of those other big things that jumps out at you. Like in the video even, it's like, if you're in Chem 130, you do not need to watch this. You can skip ahead in the video. And you're like, cool, I can skip ahead. Except you couldn't skip ahead. You had to watch it anyway, or you just hit play and walk away.
Said 12 minutes to do something.
Yeah.
Anybody notice anything interesting about our screen?
Crossed out.
Formal charges crossed out. You are not responsible for dealing with exact formal charges. Because formal charge is an interesting question, because you're responsible for aspects of it. You're not responsible for the last step. We will look at, as a first example, one of these last two. Which one do you want to look at? And we can say both. I'm fine. Both? Okay. We'll do both. Okay. Other questions?
For the bond types in the video, he came up with, there were 3 that were mentioned: the ionic, non-polar covalent, and
Polar covalent. The polar covalent we haven't reached yet in this course. Ultimately, it's still a type of covalent, so it still follows Lewis structure rules.
Will
So
that
that's all you
be
need.
part of the test?
Nope. Well, you just need to know Lewis structure. Other question?
What does the negative mean outside of the H?
Nope.
When
It's a
it
good question.
turns into the Lewis.
I'm going to dodge that question by saying I will answer that when we talk about these two.
Okay.
Other questions about it? What do you got?
So when it was talking about electronegativity, and this, you had to decide which would be the core and which element would be the outer ones. If when I was looking at the periodic table, I think the example was nitrogen and bromine. They have like equal sort of amounts of vertical and horizontal elements between them. So how do you decide which one's the most electronegative?
Okay, do we have other questions? because I'll go ahead and start with that one. It's an easier start than looking at the charged ones. Okay, let's go ahead and start with that one. Step 1, what do we do? What's that?
You add both of them together to see
What does it say at the top? You're right. What are we adding? Valence electrons. So where do we find our valence electrons? Nitrogen. The Roman numeral. What's the Roman numeral for nitrogen? 5. So it has how many valence? 5. Good job. Okay. We also have bromine. How many valence electrons does bromine have? 7, because the Roman numeral off the periodic table says 7. How many bromines are there? There's 3, so I can multiply by 3. Okay. There's no other information, so we would just run with that. We get 21 and 5 is 26. So now, Frankie, to your actual question, we need to now choose a central atom. Our central atom needs to be the least electronegative. Okay? That can bridge. Okay? And that's where things get a little wonky on us, unfortunately. Okay? What is that wonky? Hydrogen can only form one bond, ever. Its octet is 2 electrons, which then means it can never bridge, so hydrogen should never be in the middle. Well, that's an irrelevant statement because there's no hydrogens. Good point. So let's try again. Nitrogen versus bromine. If we tried to put bromine as the center atom because it is the least electronegative, we run into an issue. Our halogens are very similar to hydrogen in reactivity. And sometimes, even on some periodic tables, you will see hydrogen written directly above fluorine. Why? They all respond the same. They want one more electron. One more electron making one bond. Our halogens are not good at bridging atoms. Okay? Because they cannot bridge atoms, that means our central atom must be nitrogen. Okay? We're just saying, well, that's kind of hard to know. How would I know that? You're right. That is kind of hard to know. On a test, you could be like, I'm not quite sure what's going on here. Did I miss something? Okay? That might jog enough memory for me to be like, oh, snap, I screwed up. You're right. Nitrogen's the center atom. Okay? Problem resolved. Okay? You have to remember that sometimes your teachers don't see the same questions that you're seeing until you ask them. Now I know. Okay? So nitrogen will end up being our center atom. We'll scatter the bromines around it. At this stage, for this class, we will always have one center atom. The rest of the atoms must go around that center atom. Okay? For the Lewis structure lab, which you may or may not be doing in lab, that lab is horribly designed and needs to get fixed because there's lots of cases that they give you that don't have center atoms. Okay? For as far as the lecture is concerned, we will stick with center atoms. What's our next step?
Fill the octets.
Fill the octets by placing electrons where?
In
The most electronegative. Which one's the most electronegative? Actually, nitrogen. Again, that's hard to tell. Okay, and in this case, it's not going to bite us. Nitrogen is the 3rd most electronegative element on the periodic table. So there's my octet for nitrogen. There was a suggestion to draw lines in. I don't recommend that. It doesn't hurt anything necessarily, as we'll see in a second. Okay? But I don't recommend that. Satisfy octets first. Notice where I'm placing everything. I'm placing them on the faces of a square around that center atom. How many electrons have I drawn? 8. How many do I need?
8.
How many do I need? How many do I need?
26.
26. Okay? Somebody shouted out 5. This is cool. Let's talk about that one because that's kind of important. When you shouted out 5, someone want to volunteer? Whoever shouted out 5, why did you say 5? Nitrogen has 5 valence electrons. When does nitrogen have 5 valence electrons? When it is a nitrogen atom. Do we have a nitrogen atom anymore? No, it's a molecule. I can't use valence electrons anymore. The only reason we look at the valence is to total up how many electrons. The molecule is a potluck party. All the atoms are the people coming to the potluck. Okay, so if we had a potluck in here, everybody brought food, right? Okay. As part of that potluck, are you only allowed to eat the food you brought? No. In fact, we'd all eat everybody's food, right? We'd share it. You mean like sharing electrons? Yeah. Okay. Maybe a couple of you got me beat, but I would bet I'm probably going to eat more food than any of you. Why? I'm a greedy little bastard. No, come on. Why might I eat more food than anybody in here? It's a nice dodge. Try again. No judgments.
You're bigger?
I'm bigger than all of you. Okay, which means I'm going to eat more food than you. Okay, that is effectively my electronegativity. How my ability to consume more food is electronegativity. So if we're now going to go through and look at the potluck, I'm going to eat more of everything than anybody else will. Okay? Nitrogen, being more electronegative than the halogens, is going to do what with the electrons? It's going to eat as many electrons as it can. Well, how many electrons can an atom get? 8, because of the octet rule. That's why we use it. Okay? So I don't care how many electrons were brought to the party. That's irrelevant at this stage. We're at the party, we're just chowing down. Okay? The biggest, strongest gets all the electrons first. Okay? Once that's happened, I move to the next biggest, strongest. In this case,
It doesn't matter.
doesn't matter, they're all the same. So I can continue to place my electrons. Notice again, I'm placing them on the faces of a square for whatever atom I'm looking at. I already have a pair of electrons here, which means
They can share it. It's gonna be a line.
I'm not going to put more there because that pair of electrons can get shared between them. So there's 8 on that bromine. How do I move to the next one? I get another 8. And another 8, yeah? Cool? Questions about what we just did? Okay, how many electrons have I drawn? 26, yay! There's our structure. Okay, so now what could we go through and do? It looks a bit chicken pocky, so we might go through. No one laughed at that, must be too soon, too sensitive. Okay. We can convert pairs of electrons between atoms into a line to represent a bond. You will find that there are some chemists out there that will show every pair of electrons as a line. There isn't anything inherently wrong with that per se, except by doing it this way, what am I calling attention to? Bonds and not bonds. I have a clear way to distinguish those two differences, okay, which might be super important in a couple questions. Okay? Yes?
Why can't you just immediately draw the line? Why do you draw the dots first and then the line?
I draw the dots because I find that most people, when they draw the line, ignore one very important feature. How many electrons are around that nitrogen? 8. Most people see that line and turn it into 1, because how many lines are there? Sorry, I understand you're 3. There's 1 line there, so we tend to say, oh, it's only 1, so that's now 1. It's 2 electrons. By going through that step of intentionally showing those electrons, yes, it is redundant, but it really tries to drive home and emphasize that point. It becomes a lot more relevant, again, to organic chemistry. Okay? We now have our structure. Okay? So we could satisfy octets. How many electrons are on the bromine? 2, 4, 6, a line. 2 electrons, there's 8. Bottom bromine. 8. And 8, which means every atom has its octet. Do I have to worry about resonance? No. Do I need to worry about formal charge? No, because there's nothing written in the upper right-hand corner of my formula, so I don't have to worry about any kind of charge going into this structure. Okay? I would now have a valid Lewis structure, which I could take on to the next step, which we'll do here in maybe just a second. What do you got?
So like I was always taught that you could put down 2 lines, like a double line. Instead, is that like
No.
a technically wrong thing?
That is, well, that's actually not even technically wrong. That is absolutely wrong. Yeah, 2 lines means something entirely different, and we'll cover that in a second here. 2 lines is way different. A single line represents what? 2 electrons. What does it 2 lines mean? 4 electrons. It's an inherently different symbology, an inherently different meaning. Okay? So you may have seen it in a different context, and I'll pick a structure that we can look at that on. So the last question we could ask about it is or second to last question, what is the electron geometry for the nitrogen? So this is where you could be flipping back through your notes because you didn't memorize it yet. That's cool. Remember there's that table that I'm going to flip back to in a second, but it's going to delete all my work, so I don't want to do that quite yet. Okay. We'd look through and say, well, how many groups of electrons are around this nitrogen? We'll look at this face of the square. Are there electrons there?
Yeah.
So, one group.
2, 3, 4.
What? Right? Yeah. 4 groups of electrons. There we go. Okay. Before we go flipping back to the other thing, let's push this a little bit further, because the next step of this would be to ask not only how many groups of electrons, but what would the molecular shape be? Because this is going to get us to our electron geometry, which we haven't answered yet. I'm just going to have you hold on to that number. Okay. We could ask the molecular shape. Well, the molecular shape doesn't care about non-bonding pairs of electrons, because non-bonding pairs of electrons aren't being contributed to atoms, which means it's not part of the molecule. So when I look at the molecular geometry, I want to distinguish between bonding and non-bonding pairs. Does my drawing clearly show a difference between bonding and non-bonding pairs?
Yeah.
Yeah, the bonding is a line, and the non-bonding dots. If I drew everything as lines, oh, that's why it's dumb to show everything as lines. Okay, there's a logic behind why we do it in this pattern. Okay, so in this case, how many bonding pairs of electrons do we have? We have 3 bonding, and how many non-bonding? 1. So everybody have that for notes? Electron geometry, 4 groups of electrons. Molecular geometry, we have 3 bonding, 1 non-bonding. Yeah? Because we're about to delete it. Okay. It's okay, that's why I asked. I just want to make sure.
Wait, what are the 4 groups represented?
The 4 groups of electrons are when we looked around the faces of the square on our nitrogen, we decided, is this a group of electrons? Is this? Is this? Is this? Yes, Johnny.
Are we going to go back and...
I'll address that too a little bit later. Can I move?
Yeah.
So, groups of electrons, how many do we have? 4. So what does that mean my electron geometry is? Tetrahedral. Notice the title of the next column. Bonding electron groups. How many did I have? 3. How many non-bonding did I have? Oh, look at that. It matches lovely. Or well. It does. It just does. The molecular shape is now trigonal pyramidal. So I have 2 different ways to represent the shape of that molecule. It is tetrahedral if I just look at the groups of electrons. If I look at where the bonds are, it's trigonal pyramidal. Am I responsible for knowing those names? Yes.
Do we have to know all this for the zoo?
Yes. Okay. So, are there kind of shortcuts behind this? Okay, 2 groups of electrons, or let's just say 1 group of electrons. Okay, so let's just look at it. Here's atom A with 1 group of electrons to atom B. Describe that geometry to me. It's a line, also known as linear. Do we need to memorize the first one? No. Okay. Second one. 2 groups of electrons. So there's 1, there's 2.
Linear.
That looks linear. Couldn't I have, like, I don't know, done something like this, though? Yeah, okay. So I'm saying you don't have to memorize it. What are in those lines? Electrons. What are the electrons going to do? Those 2 lines are bonds to each other? No, they're separate bonds. So what are those 2 groups of electrons going to do? they're going to want to separate away from each other as far as possible. So I've got two things. My fists do not want to see each other. Is it likely that I'm going to do it like this? No. How about like this? No. How about like that? What shape is that? Linear. These shapes come from the electrons literally repelling away from each other. If there's only two groups of electrons, it has to be linear. Okay? What if one of those groups isn't a bond, but is a non-bonding pair of electrons? Well, dang it, I'd have a new shape. What shape is that? Do I need to memorize that one? How about for the next one? Three groups of electrons. What are all those electrons going to try and do? Get away from each other as much as possible. What is the bond angle there? 90 degrees. What is this angle? 180. Did I get them all equally far away from each other? No. So how could I spread out three things so that they would all be equally far away from each other? We buy an expensive car. I do it right? 120. With three things, right? Three things sounds like try. Where are those three things? Are they in the plane of the paper? The plane of the paper? Trigonal planar. Okay. That information is embedded there. What if one of those groups isn't a bond? Well, what's your shape now? Bent. Why is it not linear? Wouldn't it stretch out? Because what? What is still over there? A pair of electrons preventing it from going linear. So it has to stay bent. So when we look at this, the memorization really now is down to the tetrahedral. And when it comes to the tetrahedral, that is much harder to memorize. Can you draw a three-dimensional tetrahedron easily? No, that becomes a lot more difficult. You have to actually use a third dimension in your drawing. Believe it or not, you also don't have to draw it. You can use your hand. You're like, don't be, doing that to me. One bond, two bonds, three bonds, and if I could wiggle my wrist, wiggle, 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 fourth bond, there's a tetrahedron. Okay? All of your applications can come from that. You now have a tetrahedron. You get one of one group, it's actually easier to get rid of the wrist. Just chop it off, right? Okay? We would still have three groups, right? So we would have trigonal, but are they in the same plane? What? Okay? If I put them in the same plane, are all the bonds, can I drop a piece of paper where all those bonds are where my fingers are? No, so it's not planar. It's not planar, and it's a multiple choice test. It's whichever one's not planar, which will be
Pyramidal.
trigonal pyramidal. Okay? So yes, there is some memorization here, and yes, you might be feeling daunted by the amount of memorization you got to do. You're looking at a couple questions. You can accept it as just point loss. Okay? And everybody just laughs. Oh, I would never do that. Dude, everybody freaking does that. You need to do that. Right? You're going to break otherwise. Okay? Kind of makes sense? Do you feel less bad or more bad about having to memorize?
Less bad.
Okay, good. So at least it worked for you. Or you're just humoring me. That's okay. Does that make sense? Okay. So you are responsible for those. You're only looking at a couple questions. It's not the entire test. Will you see it again? Yes. You will see it again twice more. Exam 2 and final. Okay? So work with it. Get better. So we good with that? Okay. So I'm going to address, let's do the charges. Then I'll come back to your double bonds, I promise. NH4, how many electrons does nitrogen have? 5. Just so you know, the answer to that question should have been like 2 seconds. How many electrons does hydrogen have? There we go. How many? That was a horrible question. I apologize. How many hydrogens are there? 4, because we have the little 4 there. What's that plus sign mean? It means the molecule is charged. Okay, what charge is it? Positive. How does it become positive? Why not add a proton?
Because electrons are easier to move.
What did you suggest?
They'll change the atom.
Protons define the element. If I add a proton, I'm not looking at nitrogen and hydrogen anymore. Okay, the only thing I can change are the electrons. This is where things get dangerous. It's a positive charge. That must mean that I added an electron. No, electrons are negatively charged. So if I add a negative, I would become... If I add a negative, I would become negative. What is this charge? Positive. What do I have to do? Subtract. Subtract 1 what? Electron. It was 5 what for nitrogen? 5 what for nitrogen? 5 what? This 5 represented 5 what for nitrogen? Electrons. So when I'm looking at hydrogen, it was 1 electron. When I bring in charge, since it's positive, what am I doing? I'm going to subtract 1 electron. I've now accounted for that charge. 5 plus 4 is 9 plus 1 minus 1. Depending on how you want to do your process of operations there, you might need to subtract another one. 8. Okay. Center atom. Nitrogen, because hydrogen can't bridge. I'm going to throw my hydrogens around this. Electrons in pairs around the most electronegative, which is nitrogen. I would argue that you should start drawing the electrons where there are hydrogens. Somebody said something about pairs. Let's try that again. 4 hydrogens. Helps if you count right. Believe it or not, and you all laugh like, what an idiot. You all make the same mistake on the exam, and it's equally frustrating for me grading it. I go, what a stupid mistake. Make sure you know your numbers, what they're meaning. All right? So there we go. There's our structure. What do? Where we have pairs of electrons between atoms, we can turn them into a line to represent a bond. We can check octets. What is the octet for hydrogen? Octet in air quotes. 2. How many electrons does this hydrogen have?
2. 8.
How many electrons around the nitrogen? 8. 2, 4, 6, 8. Does it have its octet? Yes. Do all of our atoms have octets?
Yes.
Yes. Do I need to worry about resonance? No. Do I need to worry about formal charge?
Yes.
Is our molecule charged? Yes. Before you start losing your mind going, oh my God, you said I don't have to worry about formal charge, let's just evaluate how much you have to deal with formal charge. What is the charge on this molecule?
Positive.
That is it.
That's too much.
Okay? And believe it or not, because you're going to start going, yeah, that's too much. 9 times out of 10 grading, I have found that I ignore giving points for formal charge. It doesn't make it into my key because I don't process it appropriately. Like, that's how little weight I give it. Okay? You should still put the brackets on and drop the charge on there because that is more correct. Does that make sense for formal charge? That's what you need to do. This big old strike-through thing is if we wanted to say which atom had the positive charge. And what do you say to that? I don't know works. You could say, not today. We don't need to worry about formal charge to an atom. Don't worry about it. Okay, we only care about it to the molecule. What would the molecular shape be? Tetrahedral. 4 groups of electrons would be an electron geometry of tetrahedral. They are all bonding, so the shape is tetrahedral. Can I erase? Is there a question?
Yeah.
So that is an interesting question on how did it lose an electron. And arguably it's not losing an electron. What we're looking at is the reactivity of these species and how they aligned to make this molecule. NH4 did not lose an electron. NH4 plus, that structure, was made by taking NH3 and H plus. Well, where did the hydrogen lose the electron?
Yeah.
Why would hydrogen give up an electron to something else?
Because then it can be bonded with two.
What compound am I looking at down here? Hydrogen chloride or hydrochloric acid. Okay, we're fishing here because this is borderline stuff. We haven't talked about it. Hydrochloric acid. Acids are reactive because they have H plus. Why is this hydrogen positively charged? It lost an electron. What did it lose an electron to? To the chlorine. Why would chlorine take the electrons away from hydrogen?
Needs one reactant.
Because chlorine is, we started the whole process off of this,
Closer to
more electronegative than hydrogen. So when we look at that bond, the electron loss is because a different atom decided to take those electrons away further on down the chain. You're looking at, what you're asking about is how did the reaction happen? I don't care. Yet. I don't care yet. This is the end result. This is where the electrons are.
Okay.
Does that make sense?
Yeah.
Okay. So we could get to where it lost it. Okay. And if you push that way further, you could get all like metaphysical and religious and stuff, and I don't want to do that. The other one, charged hydroxide. How many electrons does oxygen have? 6. Getting better. Well, hydrogen? Much faster. Okay. Charge? It is a -1 charge. To become negatively charged, it had to gain an electron, which means in my total, I will be adding 1, which means my total of electrons is 8. I could go through and now set this up. This one's a little bit more straightforward because there's only 2 atoms. So what shape is this going to be? Linear. What is the electron geometry on the oxygen? Jerk of a question. We'll see why here in a second. 8 electrons. Where do I start placing electrons? Oxygen, 2, 4, 6, 8. Anywhere I have a pair of electrons between atoms, I can turn it into a bond. How many electrons are on the hydrogen? 2. The line represents 2 electrons. There's 2 electrons on the hydrogen, which means its octet is satisfied. How many electrons on the oxygen? 8. Octet satisfied. Is this an official Dunn-Lewis structure? No, because formal charge, bracket, -1. So I asked first the molecular shape. We said linear, and that is phenomenal because molecular shape is all about bonds. Since there's only one bond, it has to be linear. Then I asked and said kind of in a snarky way, that was a trick question, the electron geometry. Draw a box around the oxygen. How many groups of electrons are there? 4, which means its electron geometry is tetrahedral. Those non-bonding pairs of electrons do contribute to its electron geometry. You have to be careful with the question asked.
So you classified it as linear and then also classified it
As tetrahedral, yes.
You classified
Why?
it twice?
It gets 2 classifications. Why does it get 2 classifications? Tetrahedral corresponds to the groups of electrons around that atom. How many groups are there? 4. What's the other classification? The molecular geometry. And in the molecular geometry, I care more about the bonds. There's only one bond. The shape has to be linear.
If you look at the chart, that chart, yeah. So it has the 3 and the 1.
1 bonding. Make sure you reference. And 3 non-bonding.
So it's, wow, that's weird. Okay. Confused.
Wow.
Wait, because I'm confused.
Why which? Why does 1 bond and 3 non-bonding equal linear? We just drew it out. If we look at the molecule, there's only 2 atoms. It has to be linear. There's no other option. That's its molecular geometry. The tetrahedral, when we look at the tetrahedral, do I care about bonding versus non-bonding?
No.
No, which means all of that disappears. The only thing I'm looking at now is the number of groups of electrons around the oxygen.
So is it both one or the other? Or
So, and this is where we have to be careful. I sort of accept both, but not quite. Electron geometry is,
The electrons.
Just the groups.
which was what shape? The electron geometry
These groups of atoms.
is just the groups of electrons around the oxygen. So let's draw it back out so we can see it.
okay.
How many groups of electrons around the oxygen?
4.
4, which makes it tetrahedral. Is it linear?
No, because it's just a group.
It is a nasty word. It's confusing. We don't know what it is referencing. Okay? The it in this case would refer to exactly what we talked about before, which was our electron geometry. The electron geometry is tetrahedral. Is the electron geometry also linear?
No.
No, the electron geometry is tetrahedral. There's 4 groups of electrons. Is the molecular geometry tetrahedral?
No.
No, it's linear. There are 2 classifications for your molecule. Okay? A single classification gets a single name. Okay?
So does the question specify?
The question has to specify. If the question does not specify, yours truly wrote a crap question. In which case you could raise your hand and be like, neener, 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 you're an idiot. Right? And I might be like, no, I actually said it right there. See the words. Hopefully I would be able to say that.
You might say, yeah.
I have said that actually on a couple exams. Okay? Kind of makes sense? We get that? 2 classifications. Okay? Kind of like, am I a human?
Yeah.
Thank you. Yes, long pause there, guys. Okay. Am I female?
That's up to your discretion.
Okay. So, yeah, that was an unfortunate selection of words. But we have those classifications. We could classify things according to the type of species and then is the appropriate word sex of the species? The biological sex of the species. There are 2 classifications. But if we just went through and classified everything as male and female, that doesn't work, right? Right? You wouldn't compare me to a turtle and say, well, we're just both males. There's kind of like, that's a turtle and I'm a human. There's an extra classification. Same thing is happening here. Okay? You could think of it this way, actually. Now I'm trying to track and come up with parallels that hopefully aren't quite as bad. Of course, the wording's going to come out horrible. We're Homo sapiens. There's other Homo references, like animals, like apes are part of the Homo chain too, right? Thank you. I'm not a biologist. These electron geometries are the Homo reference. These molecular geometries are the sapien reference. That was pretty cool. I like that one. Does that make a little more sense? So it's a layer on top. Okay? How are we doing? Okay, so there was a queffence to some double bones. Let's take a look at carbon monoxide. How many electrons does carbon have? 4. 6. Where's the 6 coming from? That's the atomic number. Be careful. Name of the column is 4. So carbon has 4 valence electrons. How many electrons does oxygen have? 6. So our total electrons for this structure will be 10. Which is our center atom? Well, with only 2 atoms, who really cares? Like, it's not really relevant. We can just pick one. It doesn't really matter. So I'm going to say carbon and oxygen. And now what I'm going to do is say, your turn. Finish the structure.
Start.
A couple things come out of this. Let's draw a couple of these show up in walking around. I think I saw this structure. A lot of people had this structure. This structure is wrong. Why? Okay, there's actually a couple reasons why on this. which it only just now processed on me. The first one that jumped to my mind for it, 2, 4, 6, 8, 10, 12. You only have 10 electrons. That structure is wrong. Okay? So I saw other people do something like this. Cool, we got rid of 2 electrons. That was a nice simple fix. We don't have that exceeded or 10 electron issue. Okay? And we don't have an exceeded octet issue. So that's cool. I'm going to argue, okay, and I can easily lose this argument because you can still get the correct answer from this. But I'm going to argue that you did this wrong. What does step 3 say? Which atom is more electronegative? Oxygen. You just ate all the food, but I'm more hungry than you. I didn't get my food. That doesn't make sense. I'm bigger, faster, stronger, maybe, than most of you. I get my food first. I'm hierarchical stuff, man. I'm at the top. I get food first. This doesn't work. Okay? So, how should we redraw this? We've got our atoms separated. 2, 4, 6, 8, 10. Okay? Does that pair of electrons, does it matter if it goes here, here, or here? No. All of those are equivalent. Lewis structure doesn't acknowledge any of those differences. I put it far away from it because I know where the structure's going. Okay, so I've had enough experience with this that I kind of innately am already starting to draw the structure in a way that reflects the molecular shape. If you aren't there yet, it doesn't matter. Okay? So, if we went through to follow my steps, line, right? How many electrons are on the oxygen? How many electrons are on the carbon? 4. Remember, we got the line. It's easy to forget. Does carbon have its octet? To be an octet, how many does it need to have? 8. So it does not have its octet. Okay? This is step 6. You need to satisfy octets by moving pairs of electrons. Okay? And this is the tricky one that usually trips up all of the old school methods on how to show Lewis structure. And they screw this one up so horribly that students just go, oh, you have to memorize answers. No. Okay? If you build your structure right, the answer will come. You catch that reference? That's an old reference. So that's okay. So, how do we do it? Move pairs of electrons. This carbon is missing its octet. Should I move that pair of electrons? No, it wants that pair of electrons. That's what's keeping it not or somewhat satisfied. So I'm going to move this pair of electrons. Where could I move it? Okay. A common option is, oh, I'm going to move it to the carbon. The carbon now has more electrons. That's awesome. It's getting closer to its octet. What did you do to the oxygen? You destroyed its octet. So when we talk about moving the electrons, yes, we're moving a pair of electrons, and we're moving them towards the issue. But we can't make a new issue at the same time. So that pair of electrons needs to move to a place where both the carbon and the oxygen have access to them. You mean between them. I now have a pair of electrons between atoms, which means now I can show another line. There's our second line. That's why it appears. There's another pair of electrons. Not just because, oh, I want a double bond. No, it's there for a very valid reason. I'm satisfying octets. Okay? How many electrons are on the oxygen?
8.
8. Awesome. Carbon?
6.
Not awesome. So I'll move another one. Am I allowed to move another one?
Yes.
Whether you want to or not, you have to. There it is. There's your final answer for the Lewis structure for CO. Hi? Yes? So hydrogen's one of those weird ones where we don't have to go to the octet. Okay? Which row is hydrogen in?
The first.
How many electrons fit in the first row? 2. How many electrons fit in the second row? 8. How many electrons fit in the third row? Octets are an artifact of the number of electrons that fit in the rows of our periodic table. And you will notice that when we go through to do Lewis structures, we will only sit with octets. Right? We tend to avoid using atoms that show up in your transition area. Why? That's a really hard question in my opinion, but I did actually give you the answer earlier. So one argument is it's messy. Fair enough. When did we draw Lewis structures? What kind of bond is an OH? Covalent. Bond in NH. Bond in NH3 or NH. Covalent. Why would I not worry about any of these? Those would all be metals, which would make it an ionic bond. Lewis theory starts to run into some issues there. Right? When you jump down to that third row, and so it was interesting, you guys all said 8, and I'm kind of proud of that, sort of. What's the problem with the third row? The D block can come in there, giving us more electrons. As soon as we hit the third row, we now have the ability to promote electrons into the D block, which means expanded octets. So if you look up a structure, say for, in fact, I think even that SO3 one shows up, you might see structures on Google saying something along these lines. Well, doesn't sulfur have more than an octet? It does. Why would it do that? Formal charge on the atoms. Are you responsible for formal charge on the atoms? On the atoms? No. Do you have any idea why you would draw that?
No.
No, which is why you don't draw that. Okay, so what would you draw? You're like, that takes time. I agree, it does take time. How many electrons does sulfur have? 6, oxygen. Times 3 of them. We get 18 plus 6, 24. Sulfur will be our center because it's the least electronegative. Oxygen, oxygen, oxygen. I'll start placing electrons. Where do I place the electrons? Oxygen versus sulfur. Who wins that battle? Oxygen. Because it's more electronegative. This isn't a center atom thing. It's the more electronegative. Typically, the more electronegative on the outside. That's not always the case. 2, 4, 6, 8. Those are being like, that's a lot of dots. This kind of sucks to draw out. I know. So if you wanted to skip to the line stuff like Amanda suggested, that's kind of okay as long as you do it correctly. Crap, I didn't count. How many electrons? 24. Cool. We got 24 electrons. Oxygen. Octet? No. Sulfur does not have an octet. What does it need? It needs more electrons. So what do I have to do? Step 6. I need to satisfy the octet by moving a pair of electrons. Where's there a pair of electrons? On any of the oxygens. Which oxygen should I use? All of the oxygens become accessible for this. Okay? But I can't do all of the oxygens simultaneously. I can move a pair in and form the double bond there. I could have also done it over here.
This is the one where you have to show every example.
Give me a second. I got a lot to draw. I'm catching up. I'm trying. Okay, I think, okay. That's a little sloppy, but they're there. The double bond has appeared to move to different places because I'm using a different pair of electrons to share. Which of those answers is correct? All of them. Good. You have to draw all of them.
Oh, wait.
Yeah.
Why do we have to draw all three if you know that one of them?
You want to know why you have to draw all 3? Because when I asked which of those is correct, you all said all of them. So it's your fault you have to draw all 3, not mine.
What if we said any of them?
Why do you have to draw all of them? Each of those oxygens is equally likely to share the electrons into the sulfur, which means you have to show all of those representations. Because if you don't, you're then saying only one of those structures is valid. Okay? It would be like taking a picture of me, okay, where I'm standing here, and then taking a picture of me here and here, and then saying any one of those pictures is representative of Mike. Am I really walking around all day with my arm in the air?
No.
No, that's not representative of how I am. It might be constantly moving back and forth, and it might hover up here more frequently than other times. Okay? But you have to show all of those stages to get an accurate picture of it. Why do we want an accurate picture of it? Right? When you're taking selfies, do you take the one, keep the one where you're like, no, why not? I don't want anybody to see that. All right, I'll look pretty. Same deal, right? Except we have to show all of them. Okay? That's what's happening here. This is the concept of resonance. This concept is horribly done by most general chemistry instructors. Okay? And it's because they didn't like OChem, so they didn't see the point of having to draw Lewis structures appropriately. That's fine, because all you're doing is Gen Chem. If you have to move forward, you need to understand the concept of resonance. After 2 years of chemistry, general chemistry 1, 2, OChem 1 and OChem 2, I will still be yelling at you about resonance in OChem 2 because you keep screwing it up. It's that complex of a topic, and it's that pervasive through the subject. Okay? We really need to understand what's happening with those electrons. If you can start working yourself down that path, if you have to move into OChem, you're better off now. Okay? For those of you who don't have to do it, I'm sorry your life is so painful that you don't get to enjoy OChem. Okay? Hopefully it gets better soon and you can come back and take OChem. Okay? Does that make sense? Ish? Is there an out? Like there's an out?
You agree that just one of them is right?
So there's one possibility. Your instructor is like, no, you can just get away with showing one. That's not me. Sorry, doesn't work. Do you recognize when you first had this initial drawing that you were in this nasty boat of, oh my God, there's a bunch of different electrons that could contribute, which means I have to draw resonance? Did you acknowledge that? Yeah. Showing this work, have you proved that to me? No. Showing this work, have you proved that to me? All you've shown is you've done a double bond there. Showing all three structures, have you proved it to me? Yes. Yes. Showing this work, have you proved it to me?
No.
If those structures do indeed have resonance, you've proved to me that you understand the concept and maybe you're out of time. Okay? So there's a small out there. Okay? Very small, but it's there. Okay? So you could draw in a show your work that answer and say plus resonance. You're really relying on my kindness as an instructor. You've never had a test with me. You don't know what it is. If you don't have time, plus resonance works. If you have time, draw them out. We excited about that? Yeah, no, cool. You know, it sounds like an average class. Where do you guys have questions? It's because we covered the double now, why we have the doubles show up. It's not just because we said they exist. There's a reason for them, satisfying octets. We've got charges addressed on this. Believe it or not, we could layer in formal charge behind this. But the structure is neutral. It is. But I could use this formula to calculate formal charge in each of those atoms. You're not responsible for it, so you're done right there. Where do you guys have questions?
What would the shape be for that?
Oh, yeah. Good point. Thank you. Good call. Shape. There's my square. Right around my center atom. Are there electrons on the left face?
Yes.
Are there electrons on the top face?
Yes.
Electrons on the right face?
Yep.
Are there electrons on the bottom face? No. How many groups of electrons? 3 groups of electrons. 3 groups of electrons are all going to spread away from each other equally, generating which shape? A trigonal. Because it's 3, they will all go out in an even plane, and we get trigonal planar. What is the molecular shape? I'm waiting for the uproar on this one. The molecular shape, we go through and we evaluate those groups of electrons and decide, are they bonding or non-bonding? Is this group bonding?
Yes.
Is this group bonding?
Yes.
Is this group bonding?
Yes.
How many groups are bonding?
3.
3. How many are non-bonding?
1.
Are there electrons there?
No.
No. How many groups are non-bonding?
0.
0. What's the molecular shape? It's still trigonal planar. You're like, no way, it doesn't repeat. Yeah? I'm kind of upset that I went away from it for that reason. When we go through and draw out that structure, let's just look at the basic root here, and we evaluate that structure. You all said there were electrons, yes, electrons, yes, electrons, yes, electrons, no. But what you're asking is, in that section, aren't there 2 groups of electrons? Are they in the same face?
Yes.
Yes, which makes them 1 group. Right? Same thing would happen with the carbon monoxide. How many groups of electrons around the oxygen?
2.
2. Okay? There is a triple bond there. There are more electrons. It's still 1 group. It's still going the same direction. Okay? This is where drawing things off of a face of a square can be useful, and not trying to go through to their molecular shapes. Because if we drew it out like that, and we tried to draw a square on there, it starts to become difficult to see where the lines are. Okay? Or if you're really sloppy at drawing your stuff, okay, it becomes difficult to see where the faces are. That's why I'd recommend using the square. Okay? The square cleans that up and allows you to address it smoother. Okay? Other questions? Okay. With the short amount of time left, I'm going to be kind of more of a jerk and kind of toss this out there. The practice exam has been available. I have seen no requests for information about the practice exam. Okay. All you have to do is send me an email with all your answers, and what you get back is a list of, you did this wrong, this is why you did this wrong. Okay. You get the feedback back. Okay. I will not post answers. It's not going to happen. But if you send me your answers, I will ask you, can I post your answers? And I will post them to a discussion board that is open access to everybody. I will also post it with all of my responses to your wrong answers. Which means if you read between the lines, you can figure out which answers were right. And you can probably figure out why answers were marked wrong. That why is useful. It's a bit late to do any of that now. You're more than welcome to swing by office hours, because I will be there probably till 4 today, depending on how many people show up. I might ditch out a little bit earlier. For future exams, I would encourage you to submit the practice exam to me, complete it, and request that feedback. It does work towards your problem solves, so you can submit it for problem solves. I won't look at it to give feedback unless you specifically ask for it. Okay? That said, I hope you all do really well on Thursday, and we have a good time.